Okay, welcome everyone to lecture 6 about gamma ray astronomy. Because that's supposed to kind of help us this problem that we last week had to kind of end on this unsatisfying cliffhanger, that there are these incredibly high energy cosmic rays that come from space from somewhere, and we don't really know where they're coming from because, unfortunately, because they're charged, they get deflected on the way to Earth. So basically all we can say is that at the very highest energies, there's kind of more coming from this particular direction, but it's, we don't have the resolution to actually kind of point to a specific object. There's an interesting AGN there that is kind of suggestive, but it's kind of hard to tell exactly. You cannot really make the connection with any certainty. Another thing we saw that's going to come up later, so I just want to remind everyone, is that here we see this, what's called the knee, where one thing is the spectrum of the cosmic rays changed, so the number of particles decreases faster with higher energies, and we also see that the particles themselves get heavier. So you see kind of the lighter particles, so the hydrogen and the helium cores kind of dying out, and then the heavier ones taking over, and then it's reversing again. So keep that in mind, it's going to come up later. So we want to use gamma rays today. So what are they actually? It's basically still light. I said last week that we're going to get away from just looking at light, but here we are again. But they have such short wavelengths and such high energy that they're actually acting pretty different from kind of your normal light. So you cannot really use, for example, lenses or mirrors to redirect them. And where you kind of will find them in, well, hopefully not your everyday life, but sometimes, is in nuclear decays. So some usually very heavy nuclei will decay and will emit a gamma ray. Now, where this kind of started is in a kind of weird place, and that is at the kind of high point of the Cold War, because the US and the Soviet Union both had nuclear bombs, and they decided that for totally legit reason they needed to test a lot of them. And they kind of went overboard and ended up testing like 100-something per year. And fortunately, eventually they decided that this was kind of a bad idea. And so in '63, they signed something called the Partial Nuclear Test Ban Treaty, where they at least agreed that all the nuclear tests are going to be underground. So at least we're not blowing more and more radioactive stuff into our atmosphere. We're just poisoning the ground. Okay. Of course, they weren't just going to take each other's word for it because it was a Cold War. So the US launched something called Project Vela, which was a bunch of satellites. So these are kind of two that, for the launch are kind of stacked on top of each other. And they would orbit the Earth, and they have a bunch of gamma ray detectors and X-ray detectors on board, and the idea is that if you have a nuclear bomb detonation somewhere in the atmosphere or even in space, that would produce a lot of gamma rays and X-rays, and then you could tell that the Soviets were cheating. And they actually saw something, except they only saw gamma rays, but not the X-rays that you would expect for a nuclear bomb. So they fortunately knew immediately, like, this couldn't be any nuclear test. And eventually, they also, with the first generation of satellites, you couldn't actually tell, but eventually they could also roughly pinpoint where these signals were coming from, and they found out that they were actually coming from space. And to my surprise, this project was actually not that secret for something to do with nuclear weapons, because it was more of a kind of like a tech exploration. They were just trying to develop the technology to do the surveillance. This was not really a surveillance program. So astrophysicists got informed about this fairly early, and this was kind of how gamma ray astronomy was born. Today we don't have to piggyback on the military anymore, fortunately, and we have something like this. This is kind of right now for the lower energy gamma rays, the big experiment in the room. It's a Fermi Large Area Telescope. So this is the satellite. This is before launch. So you have the solar panels here that now are unfolded to give power. And then up here you have this Large Area Telescope. It looks kind of like this. So you have these blocks here, and each of these blocks is a gamma ray detector. And the way it works, it uses something called pair production. So this is, again, from a bubble chamber where you can see these tracks that are produced by charged particles. And here the charged part in charged particles is really important because gamma rays are not charged, so you will not see them here. But if you kind of mark the important parts, you can see here there's a positron here, and that eventually annihilates with an electron that's just in the, in the material in the bubble chamber, and it produces a gamma ray, and you can see that by not seeing anything here because gamma rays don't show up. But then a little further on, it produces a pair of electron and positron. So basically an electron and its antiparticle that have opposite charges. So in the magnetic field here, they get deflected in different directions. And Fermi uses this for something called a conversion foil detector. So first of all, what you do is you have a scintillator on top, so that if a cosmic ray gets in, it will produce a signal in here, so it's a cosmic ray. We don't care about cosmic rays now, but a gamma ray will not produce any signal in the scintillator. So you have basically an anti-coincidence detector. And then there are these conversion foils that are just basically thin layers of tungsten. And the gamma ray will then produce a pair of electrons and positrons in these foils. And then there are something called silicon strip detectors. They're kind of like a CCD sensor, except they're not pixels, they're kind of long strips. But these strips are kind of crossing at right angles, so depending on which strips get triggered, you know exactly where this track came along. And from which path these two particles, the electron and the positron, take through your detector, you know where the gamma ray came from. And then eventually you have something called a calorimeter, which is basically the idea is that you just have a big block of stuff, and ideally that stuff is a scintillator, and basically you want all your particles to dump their entire energy into this block, so you know afterwards by how much energy was dumped in there, how much energy there was in the gamma ray originally. So that's how you can see gamma rays in space, but you run into the same problem you have with cosmic rays, that at some point gamma rays become so rare that you need a bigger and bigger detector, and eventually it's not really feasible to do that in space. So if we want to measure these on Earth, we have the problem that, kind of like cosmic rays, they will not make it through the atmosphere. So instead we use something called the Cherenkov effect, which you might have seen if you saw pictures of nuclear reactors, for example. There's often this kind of bluish glow. And that is caused by that. You may remember from last week, when I talked about the Piaget Observatory, I said that these detectors here are just water tanks, basically, and they also use the Cherenkov effect. And the way it works is basically kind of like a sonic boom. If a particle moves faster than the speed of light, which sounds weird, but remember that in most materials, light actually travels slower than in vacuum. So if you have a particle that's going at almost the speed of light, and then, for example, in water, light travels at around 3/4 of the speed it has in vacuum, so then the particle is effectively going faster than the speed of light. And so you have an effect that is basically kind of like the sonic boom of an airplane. So if you have your airplane here, and you can imagine that it has an engine that produces noise. If it's slower than the speed of sound, it's just going to send out these sound waves, and it's going to be loud, but it's hopefully going to be bearable if you're not too close. For a particle, what you can imagine is it's kind of it's moving through the water, the air, and it's going to get kind of like, because there's charges in there, there's electrons in the shells of the molecules, there's nuclei, so there's little electric fields that this particle will feel, and it's going to wiggle a little bit, and every time it wiggles, it's going to send out a very, very tiny electromagnetic wave. But if it's too slow, then all these little wiggles are just going to reach you one after the other, and you're not really going to be able to see any of them. But now if we go at the speed of sound, then what's going to happen is, you can see here, that it's kind of riding its own wave. So all these little signals it's sending out, they're all going to get amplified in this front here. And that's what this the sonic barrier is, because this will cause a bunch of vibration in your plane. It's going to have a bunch of aerodynamic effects that are going to mess with you, and that's kind of a big problem if you want to go faster than the speed of sound. Now, if you go even faster, then you overtake your own sound waves or light waves. And you can see here there is this region forming here where they all overlap, because what's essentially happening is that all these sound waves, or in the case of a particle, all these light waves, are going to reach you at the same time if you're here. So instead of just seeing these little waves one at a time, you all see them all at the exact same time. So instead of tiny little signal, you have this big shock wave, and that's what this sonic boom is. That's usually so loud. Now, another important thing is something called the Cherenkov angle, because you can see that this shock front is traveling in a very specific direction, right? And this depends on how much faster than the speed of light in the material you are moving. So on the left is if we have, for example, water that has an index of refraction of 1.3, and then you can see that it's the shock front is kind of moving this direction. And if you have a higher index of refraction, so the speed of light is slower now, it's going to move kind of further off to the side. And this is something called the Cherenkov angle, and it's, for the people that are into math, it's given by the arc cosine of 1 over the index of refraction. Now, the interesting thing about this is, this means that the light is not emitted in all directions at once, but it's only emitted in a very specific direction. So we saw last week this fluorescent detection method, and the light was so weak because it's emitted in all directions. But this is brighter because it's all focused into a very specific direction. So as long as you're looking in the right direction, you can actually see this much more easily. And you use these telescopes that are called imaging air Cherenkov telescopes. So there's the biggest one right now is something called high energy stereoscopic system, which I don't think I've ever heard anyone say. Everyone just calls it Hess, after Victor Hess. And then there's Veritas in, I think, Arizona, and MAGIC on the Canary Islands. And they are basically normal telescopes. They have photomultipliers here to detect this Cherenkov light. And what's going to happen is you have your gamma ray coming, and it's going to hit the atmosphere, and it's going to produce a particle shower, kind of like a cosmic ray. And the index of refraction of air, of the atmosphere, is slightly bigger than 1, but only very slightly. So the Cherenkov angle is very, very small. It's about 1 degree. So this Cherenkov light is actually emitted almost exactly in the direction that the gamma ray is traveling in. So if you want to look at a particular source, you can just kind of point your Cherenkov telescopes into that direction, and then if a gamma ray is coming from that source, then the shower it's producing is going to basically point right at, or the Cherenkov light from that shower is going to go right into your telescope. And this is what that looks like. So this is one typical gamma ray detected by Hess. So this is from the big telescope. And you see this light from the shower. As the shower travels through the atmosphere, it's gonna, we're going to see it at slightly different positions. And these are from these other 4 little telescopes. And the nice thing about this is, if you basically drew a line through the middle of this track here, and you do this for all these telescopes, then they will all meet in the direction where this gamma ray is coming from, and that lets you reconstruct the direction of the gamma ray fairly precisely to about 0.1 degree, ideally. But you might have noticed the problem with this, and that is there's also cosmic rays. So how do we know that what we're seeing, that this shower is from a gamma ray and not a cosmic ray? And cosmic rays are actually much more common than gamma rays at these energies. And for this, we unfortunately have to go a little bit into particle physics theory. And there's 4 fundamental forces in the universe. We're just caring about 2 here that play a role in these showers. And first of all, there's the electromagnetic force that is fairly strong. And most importantly, it has a pretty long range, right? We can, if you take out a compass, you can feel the magnetic field of the core of the Earth that's hundreds or thousands of kilometers away. So it can have a pretty long range. And it also affects all charged particles. So it will, for example, affect electrons, it will affect nuclei, and it also affects photons. So because it's not quite that strong, but it has a long range, what it's doing in a shower is that you will have many interactions, but each individual interaction is going to be fairly weak. So you're not going to have a lot of energy transferred to any new particle that you're creating. Whereas the other force is the strong nuclear force, which, as the name implies, is much stronger than the electromagnetic force, but it's also very, very small range. So what this is going to do in a shower is there's going to be a lot fewer interactions, but each individual interaction is going to be much, much stronger. And the important thing here is that it only affects particles called hadrons, which in our case, the important part is that protons and neutrons, which make up a nuclei, are affected by this, whereas, for example, gamma rays will not be affected by this. So because of this, the showers that you get from gamma rays and from protons are actually looking quite different. So this here is from a gamma ray, and because gamma rays will only interact via the electromagnetic force, and this will almost always only create electrons and positrons, which also are only affected by the electromagnetic force. What you end up with is a lot of fairly small interactions, so you don't have this kind of fuzziness. You have a bit of fuzziness, but it's a fairly straight shower with a lot of particles. Whereas for a proton, you have the strong nuclear force affecting it. So what you can see here is that it's a lot kind of, I don't know the right word for it, where you can see there's a lot fewer individual particles in there, and there's also a lot of times where you can see that kind of it's almost like there's its own branch here, because that's one of these rarer strong interactions where just a lot of this particle that got created just got a lot of kind of kick to the side, and you can see this in the Cherenkov telescopes. So on the left, is your shower from gamma ray, and it has this nice little, this nice thin line. Whereas here you see the shower from a proton, and you can see because it's so fuzzy, it has just this big blob. So with this, just looking at kind of the shape of the signal you get, you can actually identify a lot of these cosmic ray signals, and you can just kind of get rid of them and just pick out the signals from gamma rays. Except that's still not going to give you like 100% purity. You're still going to have some signals from cosmic rays in there. So what you also use is the fact that because cosmic rays are deflected by magnetic fields, they're coming from basically all directions the same. We saw that last week, right? And especially on these kind of smaller scales, you see the exact same amount from any direction. So what you're doing is, if you have your source here that you want to look at, you just look at two positions, or sometimes more positions, kind of somewhat close to it, but far away that it's not going to interfere with it, and you just use that to estimate your background of cosmic rays. So what you're really looking at is how much more than kind of the average around it does a source actually produce. And from that, you can get a pretty good idea of how many gamma rays it produces. Okay, now we can see these gamma rays, but what does this have to do with cosmic rays? What's the connection here? And we have to go back to our pion decay again. Last week I talked about how in these air showers you have charged pions being produced, and that those decay into these muons that we see. But there's also a different version of the pion, and that's a neutral one. And you can see that in this bubble chamber here. Again, so because the neutral pion is neutral, you cannot see it. But what you can tell afterwards is that here it decays into two gamma rays, and then one gamma ray goes this way and produces an electron-positron pair over here, and then another one goes this way and produces them here. So you kind of have to know what you're looking at, but from just kind of figuring out the energy each of these have and kind of the direction, that these electron tracks are going, you can tell that this must have been a pion. And so if we have something that's producing cosmic rays, then at least some of these cosmic rays are going to crash into stuff, and at least some of the time they're going to produce these pions, and then these pions will decay into gamma rays. So if there is a region where there's a lot of cosmic rays being accelerated, then that region should also produce a lot of gamma rays. And so if we can see these gamma rays, then hopefully we know that that's where the cosmic rays come from. Yes?
Can you explain how this figure is obtained? Is it how imaged and something?
So
can you explain how these are imaged?
Yeah, it is pretty similar to how a cloud chamber works, where you have, so in a cloud chamber what happens is you have these ionization trails, and that's where, like, for example, like water vapor will solidify, and you have clouds being produced. This is kind of doing the opposite, so you have a liquid, and that's very, very close to its boiling point. And if you then have a charged particle going through, what's happening is that it's going to form little bubbles. And these bubbles are going to expand, and eventually they're big enough that you can just photograph them. So this is actually just a photograph. And that's kind of how they did particle physics in like the 50s and 60s. Today
Is this obtained by actual experiment? Is it
yeah. This is...
So the detector that detected this image, could you explain how it detects that image?
It's a photograph, basically. There's someone sitting there with a button, and every time something interesting looks up, he has to push, and then there's a camera. So these
are traces of a particle.
Yes.
And it's imaging the particle.
Yes. So this is, I mean, if you're fast enough, you could see this with your own eye. Okay, so that's one way you can get gamma rays from cosmic rays. There's actually another way you can do it, and that is Compton scattering, named after the namesake of also this lecture series. And what Arthur Compton noticed is that if you have a piece of metal and you shine a light at it, and the light gets reflected off it, then this light will change its frequency a little bit, because what's happening is in a metal, electrons are pretty free to move. So they can go wherever they want. And so this photon will kind of bump into an electron in there and give it some of this energy. So the photon will lose some energy and have a longer wavelength, and the electron will gain a little bit. So that's called the Compton effect, but we can also reverse this. So if you have a high energy electron, or another particle, but it's the strongest with electrons, then it can also bump into a photon, and then the electron gives some of its energy to the photon, and then you have a higher energy photon. And if this is a cosmic ray with enough energy, then it can actually bump a photon that's even just like at radio wavelengths even. It can bump it up all the way to high energy gamma rays. And it's the same idea. If you have your cosmic ray source, then some of the time, it's going to bump. These cosmic rays are going to interact with photons around there, and they're going to produce gamma rays. So again, same idea. If we can see these gamma rays, we know there have to be high energy cosmic rays there. So if we now just look at the sky with our gamma ray telescopes, this is what we actually see. So this is taken with Fermi. Nice thing about space missions is usually they can see the entire sky. And, well, you can see, first of all, you see the galaxy very well. So this is the center of the galaxy, is right in the middle here. So a lot of gamma rays are coming from the galaxy, unsurprisingly. And then you have a bunch of stuff that's outside the galactic plane. So these are almost all, we're pretty sure these are all, not all, but mostly extragalactic sources. And in particular, for now, I want to look at three of these. One is Cassiopeia A, which is kind of this little dot here. There's the Vela system, which is kind of its own thing. There is a pulsar there. There is also a supernova remnant there that just happens to be in the kind of in the same direction. They're actually very far apart. One is much further than the other, but they just happen to be at the same spot in the sky. That's why it looks so bright. And then there's a Crab nebula that we talked a bunch of times about. And if we kind of zoom in on these with our gamma ray telescopes, we can see for the Crab nebula, because it's pretty far away, we just kind of see this blob here. But in the Vela system, there's this thing called Vela Junior. And you can see that it has this kind of bubble look in it. Right in the middle, there's not actually that much gamma rays coming from it, but then on the outside, you have this kind of ring of gamma rays. By the way, this has nothing to, the name has nothing to do with the Vela satellites. It's just a pure coincidence that they have the same name. Now, with the Crab nebula, this is what it looks like in mostly visible wavelengths. If you really zoom in into the center here, what you see here is this is a neutron star. So it's kind of similar to a white dwarf. It's an extremely dense object that was left from the supernova that produced this Crab nebula. And if I turn the video on again, you can see there's this stuff moving out from the pulsar, right? You see these kind of almost looks like waves coming out there. So this is the reason why the Crab nebula is, or the kind of object that the Crab nebula is one of, is often called the pulsar wind nebula, because you have this flow of particles coming out from the pulsar and kind of crashing into the surrounding medium. And I cannot skip ahead. There we go. Now, for Cassiopeia A and Vela Junior, these are supernova remnants. So what happened here at some point is a star exploded, so you had a supernova. That also is how the Crab nebula was started. But what you have in these supernova explosions is that you can see there is the star used to be here in the middle, and then you have this kind of structure, this kind of bubble that's what's left of the star basically expanding. And the same with the Vela Junior. So this is from, I think this is radio, so you again see this kind of like bubble-like structure. And so that is, what used to be the star being ripped apart. And for some reason that we actually don't know, the Crab nebula doesn't seem to have this finely defined shell. And no one really knows why it's missing. Now, what we saw a couple of weeks ago is that a lot of superstars, before they explode, they will actually shed a big part of the atmosphere. The most extreme stars to do this are called Wolf-Rayet stars, where you just have this giant outflow of stuff out of the star. But this is we think that basically every star that goes supernova does this. Our sun will also basically do this at some point, even though it's not going to be a supernova. And so what we think is happening then is that you have the star shedding its outer atmosphere, and then when it explodes, kind of the parts of the stars that get ejected much faster are going to crash into this atmosphere that was shed earlier. And what's going to happen is, well, first of all, it's going to heat up because you have a bunch of gas crashing into other gas, and that's why Cassiopeia A looks really bright in X-rays, because very hot gas will produce X-rays. And you can see again, you have this outer shell that's really, really hot. And what you can also see that is that this outer shell also produces a lot of radio signals, which is usually a sign that there's electrons moving around really quickly. And I see a question.
Thank you. What produces the initial shedding of those layers before the supernova?
It's essentially the star goes to a more efficient fusion process, and it's basically getting so hot that it's not it cannot, gravity is not enough to hold to its gas anymore.
Is that fusion in the shell or in the core?
No, it's in the core, but eventually the heat makes it out. Yeah, so we have basically, we have the 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 fragments of the star crashing into its atmosphere, and that's going to produce a shock wave. And we think that these shock waves actually produce the cosmic rays that we're seeing, at least at the lower energies. Well, first of all, because we see the gamma rays coming from this. And second, there's actually a really well understood process that can produce exactly what we're seeing with cosmic rays. And there's something called Fermi shock acceleration. And the kind of picture I want to keep in mind is, imagine you take a tennis ball and you throw it on a highway, which you should never do, so let's just imagine it. But what's going to happen is, of course, cars are going to bump into this tennis ball. And every time a car hits it, it's going to gain some energy. Well, that is if, if a car hits it head on. If it bumps into the back of a car, it's going to lose energy. So if, the ball stays on the highway a bunch of times, cars are going to keep bumping into it and giving it more and more energy as long as it's a mostly head-on collisions, until eventually it's going to fly off the highway, and then you have a high-energy tennis ball flying through space, basically. There's a question? It's basically because the center of the star gets so extremely hot. Because you have the outer part of the star kind of falling into it, and if it's it's like the part that's falling is getting faster and faster until eventually it crashes into kind of the rest of the star, and so that's going to heat it up extremely, and it's also going to produce a lot of pressure, and from that you can suddenly have really a lot of fusion kind of igniting all at once. So it's basically like a giant fusion bomb going off.
Yeah, so it's like super fusion plus build-up of
yeah.
photons.
Yes.
Okay.
Yeah?
These images here show a star that exploded.
Yes.
And this could be the cloud that is the result of the debris
Yes.
of the star. And these here images do not evolve in like seconds or minutes or hours. It looks they are there for very, very, very long time. And their image did not change much over so much time. Is it possible that they are in the process of accretion? And some of these higher density and lower density areas could be like became denser than others. It is just in the process of accretion. Is it possible to think of it like this way?
Well, so we can tell that they're expanding. One, because with some of them, when they're fairly close, you can actually just see them. If it takes years till you actually notice a difference, but you can see them get bigger. And you can also measure the redshift from these ejecta, and you can tell that they're moving towards you.
Internal redshift? Like, is it they are expanding from their own center?
Yes. I mean, you're going to see more of the stuff that's pointing towards you than the parts pointing back to you. So if it's not redshifted, it's blue shifted, of course, because it's moving towards you. And from this blue shift, you can tell, you can tell how fast it's moving. And also, for example, for the Crab Nebula, that exploded in like 1050 something, and we know that because Chinese astronomers saw it and wrote it down.
Another question is about their size. Do they have comparable size, or are like some of them could be the size? I don't know. They are bigger than our sun because they are bigger. Clouds.
I mean, the older they are, the more the bigger they get. So yes.
So could you say the range of
I don't have a number in my head. I would have to look it up. But it's several light years. These are pretty big structures. Okay, yeah, shock acceleration. So, again, keep in mind if you throw a tennis ball onto a highway, it's going to bump into cars, and each time a car hits it head on, it's going to gain some energy. And we think that basically the same is happening in these shocked regions, because what you have is you have your surrounding medium, so it can actually be like just some gas that happens to be near the star, or it can be this outer layer of the old atmosphere of the star. And then you have these ejecta from the supernova remnant, and they're going to crash into this medium at rest, and it's going to produce a shock front. And now these ejecta are very fast, but this shock front is going to move slower than the ejecta crashing into it, because it's gas being compressed. So now if we kind of change our perspective and we kind of imagine we're sitting on this shock front here, then what it's going to look like is the SNR ejecta are still going to crash into us, but it also looks to us like the surrounding medium is also coming towards us. And now you have your particles in there, and so this gas is actually very thin, it's much thinner than our atmosphere. So particles that are trapped in there are actually not really going to collide with kind of this gas that much, but because it's really hot, it's ionized, you actually have pretty strong magnetic fields in there. So these particles are going to get trapped in these magnetic fields, and they're going to kind of move along mostly with this gas, but they're kind of going to diffuse around. But every time they cross this shock front, they're going to gain a little bit of energy. And the amount of energy, if you kind of do the math, it turns out the amount of energy that it gets every time it crosses the shock front is proportional to the energy it already has. So this is, if you think back of high school math, if you have some money and you get some amount of money in proportion to how much you have, right? That's how interest works, and you have an exponential growth. So if you have this particle crossing the shock front a bunch of times, it can gain energy fairly quickly. And it's going to do that quite a lot because, no matter which side you're on, the medium you're drifting around in is always moving towards the shock front. Well, sometimes, depending on where you are, it also looks like the shock front is moving towards you, but the idea is the same. You have a tendency to go back to the shock front. But there's also, because this drift is pretty random, there's also always a certain chance that you're going to escape after a cycle. So you have an exponential growth with a number of cycles, but you have a random chance that it will just going to stop after any cycle. And if you do the math of what spectrum you would expect, it turns out you actually get this exact power law spectrum, or almost this exact power law spectrum that we see the cosmic rays having. And the nice thing about this is also you don't actually have to make a lot of specific assumptions about what these ejecta actually are. Basically, all you need to assume is that this shock front is a very strong shock, where the shock front is moving much faster than the speed of sound. If you do that, you actually get something that's pretty close to the spectrum we're seeing. And now with this, eventually, yes.
This is the free space, the surrounding medium.
No, the surrounding medium is also gas. That's, for example, the atmosphere of the star that was shed before the supernova.
Okay, it's not outside.
No, it's still like some gas cloud or something. It can also be just like a gas cloud that's hanging around there. And now with this, this whole thing kind of makes a lot more sense, right? We see this spectrum because well, that's kind of what you just get out of doing the math for these shock fronts. It also explains why there's really no features in the spectrum, because it doesn't really matter how exactly this supernova remnant looks. It's a very generic process. So you have two different supernova remnants. They can look very different, but they're still going to give you the same spectrum. So all, even if you have multiple sources that are all a little bit different, they're all going to give you basically the same signal. And we can also see that now this whole thing here with the cosmic rays getting heavier around the knee makes sense, because this acceleration process only works if you can actually trap your particles inside inside these shocks. And remember that the radius of a particle in a magnetic field depends on the energy and on the charge. So if these particles gain more and more energy, at some point the deflections from the magnetic field are going to be kind of too little to still keep them in the inside this acceleration region. But of course, if you have a heavier particle that has more charge, then it's going to be easier to keep them in this region. So if you go past this energy where you can no longer be trapped inside your acceleration region, it's going to happen to the lighter particles first, and that's what we think we're seeing here. We see, first of all, helium and hydrogen have too much energy to stay inside the supernova remnant, and then they drop off, and then eventually the heavier elements can go a bit longer, and then eventually they drop off. Then eventually we think that there's a second kind of source that produces them, because if we know roughly how big the supernova remnants are, we have a rough idea how strong the magnetic fields there are, and if you do the math, you actually expect this to happen roughly at these energies. So that's why we're pretty confident that most of the cosmic rays up to the knee here are from mostly the supernova remnants. There's the question?
I noticed something about this data. Why are there so little protons being detected in the satellite, if I'm reading that correctly?
Which one? This one? Or this one?
Orange. The orange X's, that says proton satellite, right? Am I reading it right?
This. So, yeah, I mean, this is, at lower energies than where you see this transition. So you have mostly protons here. So protons are still like the dominant contribution to cosmic rays.
I know, but look. All right.
Oh, you mean this here? Or
No, I mean like
you mean these?
the orange, yeah.
These here?
Yes, I was wondering why there are so little of them, or why they're spread out.
Oh, that's just from like a particular experiment, and they just measured it at these energies. It's just, they didn't bother to measure it at these energies.
I guess it's like, all right. So.
It's like some of these are from experiments that have like very specific goals in what they want to measure, and so sometimes they take data at different positions. So it's just what data is available.
That makes more sense.
Yeah. Okay. Yeah. So now we have a good reason. We have a decent idea of where the knee is coming from, but and we think most of the cosmic rays come from these supernova remnants, because first of all, there are quite a lot of these supernova remnants in our galaxy, and you can if you kind of model how many cosmic rays you think such a supernova remnant can produce, and you can kind of estimate this pretty well with the amount of gamma rays you see, they should they can produce enough cosmic rays to explain the vast majority of what we're seeing. But the interesting thing about these astrophysical shocks is that they're actually pretty common. So this is just some objects where you can see this. So this here is also a pulsar, but it's kind of moving pretty fast through interstellar medium. And so you have what's called a bow shock, because it kind of looks like the bow of a ship, kind of moving through here. So this is, again, I think this is radio waves. So you can see this kind of shock front here just from the, the pulsar is, this is a pulsar. The pulsar is kind of shooting out particles, and these then also crash into the surrounding medium. The sun also, by the way, produces a bow shock, so it's pretty weak. We have these active galactic nuclei that we mentioned a few weeks ago. You have these jets shooting out, but at some point, they have these termination regions where you have what's called a termination shock, because you have these jets crashing into gas clouds at the end. We also think that these gamma ray bursts that I started this whole lecture with, that Vela saw, we're not actually 100% sure what it is, but probably what it is a supernova that is, or it is kind of like a supernova in the sense that it's the death of a very, very massive star. But in that case, the star is probably so massive that it directly collapses into a black hole. And so what we think is happening is that around this black hole, you have these jets forming, kind of like these active galactic nuclei. But a lot of the outer part of the star is still around. So you have this jet kind of punching through the outer layers of the star. And yeah, that's going to give you quite a big shock. You also have sometimes galaxies that look kind of weird. So, you know, this is a galaxy that has this kind of really weird shape. And probably what happened is that two galaxies collided. And what that does a lot of the time is it will disturb the gas that's in the galaxy, and you get what's called a starburst galaxy, because these gas clouds get disturbed, and a lot of them are going to collapse into stars. So you just have a lot more star forming going on than you have in normal galaxies, and that does two things. So first of all, you have a lot of new stars, and a lot of these stars are going to be really massive and not live long. So these starburst galaxies tend to also, you know, not have only have a lot of new stars. They also have a lot of stars that die in supernovas. So you also have a lot of supernova remnants in there. But you also have just a bunch of gas clouds colliding, and where they collide, you also get these shock fronts. And so we think that some of these things probably, most likely, you know, these three kinds of classes, probably not the bow shocks, are probably responsible for the very highest energy cosmic rays. So, you know, we could just take our gamma ray telescopes and just look at them and see if they produce higher energy gamma rays, because, you know, if you have higher energy cosmic rays, you expect higher energy gamma rays. Unfortunately, there's a problem, and yeah, this is a little awkward, because during this lecture series, I kept going on about how if you have light, like how two light waves will never interrupt each other. You know, they will just pass through each other. Turns out I lied. But I only lied a little bit, because they only interact if they have extremely high energy. Because if you have a very high energy gamma ray, and you have for example, like an infrared photon, if that gamma ray has enough energy, these two photons can actually produce an electron-positron pair. And that's going to basically, first of all, it's going to destroy the gamma ray. And even if, you know, that electron-positron pair then produces a new gamma ray, that gamma ray is not going to have enough energy. So at higher energies, like kind of at energies past where we saw this transition from the of the knee, where we think the the extragalactic sources become important, that's unfortunately also when the universe kind of starts getting intransparent for gamma rays. So if we look at some galaxy really far away, we can unfortunately only detect the lower energy gamma rays. So for the ultra-high energy cosmic rays, unfortunately gamma rays are not going to be the answer that we would like. We see gamma rays from these extragalactic sources. We see gamma rays from AGNs. So we know that there's some particle acceleration going on there, but unfortunately gamma rays cannot tell us if these accelerations actually go up to the very highest energy. So for that, it would be really nice if there was another particle that gets produced by ultra-energy cosmic rays that actually can make it all the way to us. Unfortunately, there is. And that's what's going to come up next week, and it's also what I'm working on. So the experiment I'm working on consists of a bunch of radio antennas that we drop into the ice in Greenland to detect particles called neutrinos that can hopefully, when we see them, answer this question. But yeah, I'm going to talk about that next week, and look forward to that. I see a question back there.
For the supernova that was producing that standard emission, are those all types of supernova or just a specific?
It's probably, yeah, it should be all of them, I think. I mean, you just need kind of this explosion going on. That you get that whenever a star explodes. I'm not entirely sure if you have the 1A supernova, so you have a white dwarf. I'm not entirely sure if you would necessarily have like a surrounding medium that's dense enough for the shock front to form. It's probably kind of you have to get lucky about that. And there's also an interesting thing that, for example, the Crab Nebula doesn't have this like very clearly defined outer shell, and there are quite a few supernova remnants that don't have that, and we don't really understand why that's missing there. It might actually be there. It might just be too faint to detect. We don't know. But yeah, at least most supernovae will produce you these acceleration zones. Yeah?
Do we theorize white holes could produce gamma rays? Though we've never seen one, but I mean.
I honestly don't know enough about white holes to answer that. I don't know how they would accelerate stuff. Yeah?
Question. Supernova is explosion of a big star, and the star says loses about 40 to 60% of its mass. And it shrinks to about 100 kilometer radius, like this.
Could be, yeah.
Whatever, and has a zillion times density. But its mass is still about 50% of the original mass. So in this case, in space, is going to project less gravity than the original star. So why do we call it a black hole that is going to gobble everything?
Well, because it's actually not so much about the mass of it, it's more about the size of it. It's
as a space, in space.
Yes.
Space, it's really, it is tiny place. If you want to consider its original radius, original volume there, okay? Beyond that space, this is what gravity that counts. If it's going to really attract any matter from there.
Yeah, so
in this case, it has to project less gravity beyond the original radius. Less gravity than the original.
yes, that's true. So if you like replace the sun with a black hole with the same mass, like the planets would move the exact same way. The difference is that if you get really close to a black hole, then the gravity gets extremely strong. And with the star, because the star has a certain size, you just can never get that close. So the kind of the event horizon of a black hole is much smaller than the size of a star of the same mass.
What would make you get closer to the black hole? I mean, whatever makes you to get closer to the black hole that is produced later is the same thing that will make you get closer to the star, to the original star.
Well, the thing is, you're going to bump into the star before you get close enough to the star is larger than kind of how close you would have to get to the black hole to really see a difference. It's about how compact the object is, not really so much about the mass. Yeah?
When you show the picture of the galaxy and you show where the...
Yes. Hang on.
This,
yeah.
So what does blue mean here?
Oh, it's...
Blue mean, how much of blue is we don't know, and how much of blue is it's not there?
Blue is, so it's, the thing is, you have to, where did I do it? You have to do this compared to a background, because you can get rid of most of the cosmic rays by kind of looking at the the shape of the light you see, but cosmic rays are so much more common than gamma rays that even if you can get rid of 99% of all the cosmic rays, you still have a lot of them in there. So you always have to compare this to some background. And so what blue means in this picture is basically we don't see more gamma rays than on average.
And I guess my point is, how much of that is we couldn't see it?
I mean,
how much of it is
That could be. I mean, with these, basically what you can always say, if there is a source, it has to be weaker than so and so. Yes. So yeah,
It seems as though the farther we get away from this equator, the harder it appears to see it.
yeah, that's definitely true. I mean, but it's also just that there's just less and less there because once you go away from our galaxy, it's just emptier.
It's emptier.
I mean, yeah, because most of what you see here is stuff that's inside our galaxy. Here, and here is just these are then mostly extragalactic sources, and there's just there's a lot of them, but they tend to be really far away, so they tend to be pretty weak. Yeah.
So in this picture, then, a galaxy is kind of like a platter. So if we're looking to the longitude of the platter, that's why it's all on the equator.
Yes. So yeah, that's why you see this disk shape because it's we're in this disk. That's why it's this kind of thin-looking line. Yes. Yeah.
I was wondering on the one where they had like the gamma ray compared to the proton. I was wondering, there's like
This one?
yeah. I was wondering like in those like hexagon thingies, there's like a couple of like light blue hexagons in each one. Is that a hexagon? I can't.
Yeah, it's hexagons.
There's like, is it just like a quirk of how they graph it that a couple of those have like little red pixels inside?
Oh, you mean like here? There's a red one, and then
No, there are like a couple of like little light blue.
you mean like these, for example?
No, like aside from the line.
Oh, here? Oh, you mean like something like this? Yeah.
Yeah, but with like a red one, with like a red center. I was wondering if that's just a quirk of how.
Oh, you mean something like this?
Yeah.
Um,
Is that just a quirk of how they graph it, or is that like
yeah, actually,
super high energy particles that got deflected?
yeah. I honestly didn't notice that there was this purple X in there. I don't know what it means. I mean, you always have some background from light that's coming from what else? Like,
I guess it's just a weird way of graphing it.
yeah,
Like that.
it's. I mean, this X probably means that there's something wrong in the pixel, I would guess. And it's also just like some of them are brighter just because you have kind of coincidentally you have just light from somewhere else. You have the moon somewhere, and then it reflects off something, and then it goes in there. You always have like a little bit of background noise with this. That's just inevitable. Yeah.
Yeah, how close does a supernova have to be to Earth to be danger to life?
Good question. So if it's kind of in our galaxy, it's not necessarily a problem. So I think if it's like kind of, it has to be like fairly close to be like kind of, everything dies all at once. For that, it has to be within like, I think like thousands of light years or something. There is an idea that one of the big 5 mass extinction events. That's what. Yeah, could be. Yeah. I think that's the one. That might have been caused by something like a supernova. Probably, I think gamma ray bursts get blamed for that. That's usually what you read.
The gamma ray burst is when the supernova has a particular orientation.
We're not 100% sure what gamma ray bursts exactly are, but it's probably this kind of supernova where you have a collapse into a black hole directly instead of a neutron star. You knew it, Ordovician. Ordovician.
That's from, what is it, 440 to 4...
Yeah.
Something around the 400 million years.
That's
right after the Cambrian.
Yeah, it's called the Big Five. There were like 5 really big mass extinction events, and it's like the second or so of those.
It was the first one.
Ordovician extinction event, I think. I'm not a paleontologist, unfortunately.
Yeah, I think that was the first
Before the dinosaurs, right?
Yeah, it was
Oh, yeah, way
pretty.
before
Yeah.
And what is the evidence that makes them think it's that?
I don't remember, to be honest. just remember it's been a hypothesis. Yeah. Yeah.
They say that supernova or the collapse of the star happens, I read sometimes in a second, and explosion can happen completely in 100 seconds. And you just said that they are frequent, they happen a lot, okay? Because they are the source of all these cosmic rays. Well, in this case, did you detect anyone in process of being, becoming supernova?
Well, so frequent means for a galaxy the size of the Milky Way, it's about 1 every 100 years on average. But these supernova remnants, like they can kind of survive and accelerate particles for thousands of years. So it's, they are very long-lived. And I'm not, so I don't think we've seen one that's like recently that's directly in our galaxy. And if it's kind of too far away, you cannot see these supernova remnants directly. So I don't think there's one that we've seen like right after it exploded, if I remember correctly. But we have, for example, the Crab Nebula, where we see it 1,000 years later, at least.
Wasn't there one from one of the Magellanic Clouds?
Yeah, right. There was one. Yeah, there was in 86, 87. There was one. Yeah. I don't know if we have found the supernova remnant of that.
Was this recorded?
That was.
The one in 86?
That was in one of the Magellanic Clouds. That should be visible. I have to check if we can actually see it.
I think the neutrinos hit us before the light, right?
Yeah, that's going to come up next week.
Okay.
Yeah.
In billions of years from now, is it possible that our sun will become a supernova? And
it's not heavy enough to be a supernova. It's gonna basically become a red giant and expand, but it's not gonna you're not gonna have this violent supernova explosion. It has to be more massive than our sun is.
But it's already produced the planets by sun. The planets produced by the sun. By what process?
I mean, it's probably basically a collapse of a gas cloud, and some of that material or most of that material ended in the sun, and then some of it.
They were ejected as a cloud from the sun?
No, it was. They probably formed at like roughly the same time, and it's basically you start with a gas cloud, and that collapses, and most of it ends up collapsing into the sun.
At the same time?
Yes, roughly. Yeah.
I thought red giants did eventually explode.
Not necessarily. Not all of them.
I mean, do they just, most of it just sort of cease to be dense enough to really be considered a star?
So what usually happens is eventually they run out of fuel, and then they kind of slowly cool down, and it's called a brown. Not a brown dwarf, but they're really hard to find because they're not shining anymore. But you just basically have them kind of fizzle out and slowly get colder.
All right.
Yeah.
Giant stars, like you mentioned, Wolf-Rayet stars, they theorize because they're so big that they could condense directly into a black hole without exploding. But during that process, would they theorize it could release neutrinos or gamma ray bursts or some form of
Yeah, so we think that this collapse directly into a black hole of a really massive star, that's probably what most gamma ray bursts are from.
Oh, really?
It's kind of hard to prove because you don't know, you cannot go like, oh yeah, there's definitely going to be like gamma ray burst coming from there. Let's see if we find something there. And they're also, that usually, fortunately, from really far away. So, they're too far away to actually look at individual stars. So it's kind of hard to prove. But if if you model what that should look like, you expect something like a gamma ray burst, so we think it's probably where they are from. But
Do you
it's
understand the mechanism of how that would happen in a fast collapsing giant star?
how. Oh, yeah, it's basically the same thing as shock acceleration. So you have, hang on. So you basically have a jet that's, kind of like you see with an AGN. It's, it's a black hole, it's just a bit smaller. And the star is collapsing so fast that like the outer part of it is still around. So you have this jet punching through kind of the outer part of the star. And from that you get these shock waves. And also probably kind of, you probably have an accretion disk in there where you also have collision.
All these pictures are real pictures, or some of them are simulation?
This one's simulation, the others are real.
And that one on the upper right?
That one, that's real, that's radio telescope, yeah.
This is real?
Yep. Okay, I don't see more questions. Then I see you next week.